afternoon. My name is Azira. I'm from Malaysian Rubber Board. So my presentation today entitled Arrangement of Carbon Nanotubes in Natural Rubber Nanocomposites via Atomic Force Microscope. So this is my presentation outline. I will start as for the introduction of carbon nanotubes. Then I'll bring you to the experimental use in this world. So then I will discuss on the results and discussion. Then I will discuss in depth about the surface analysis as well as the film formation. Then I will conclude my work in the conclusion part. So to begin with, so what is carbon nanotubes? So carbon nanotubes can be visualized as a graphene layer rolled into a cylindrical consisting of a planar hexagonal arrangement of a carbon-carbon bond. So they are actually bonded with the van der Waals. So their outstanding properties are actually the consequences of this unique bonding arrangement combined with the topological effects. So such as the zigzag and as well as the armchair, we actually contribute toward the whether they are conductive or they are non-conductive. That is actually required by rolling up the sheets of this graphene into the cylinders. So actually during the growth depends on the synthesis method, whether you synthesize using the chemical vapor deposition, arc discharge, or also on the laser ablation. So they can actually assemble either in the concentric tubes, whether it's going to be a multi-wall nanotubes, or also a single or individual structure, which is on the single wall nanotubes. So their diameter ranging from nanometer to a tenth of nanometer, which is actually on the width of the tubes, or also on the length, which actually can grow from several micrometers to even a few centimeters. So in this method, so this is the synthesis method that I would like to share with you. So we have tried out different type of technique here. So the different technique actually to attempt to optimize on the nanotube dispersion of the different type of the polymeric media used. So in this work, we use the polyisoprene or actually the natural rubber latex. So this is actually include this a few types which I discussed here, which is a solution mixing. We can use either by using latex or also on the dry rubber method. So if you are using the nanomaterial, so you need to use the sonication. So it's quite crucial to get a good dispersion. So we also use on the coagulation, melt compounding. Usually we use this in the dry rubber method. In situ microemulsion polymerization, as well as on the oxidation, chemical functionalization, and also on the chemical functionalization here we use on the hydroxyl or the carboxyl method, and also this method is actually quite crucial because the ultimate goal of this processing is actually the ultimate goal of this processing to get to separate out the individual nanotubes in order to get a homogeneous dispersion throughout the matrix for the chemical functionalization that we introduce into the polymeric media. So why? Because we need to get some addition between this nanotube and as well as for the polymer that we use in able to get the effective stress transfer at the polymer filler interface. So this is the properties of the carbon nanotube that we intend to get in our product. So the carbon-based material that used here is actually carbon nanotubes. We also explore on graphene. So the target market is actually for the composite material. So why we are interested? Because the superior physical properties and as well as the high mechanical strength and also the exceptional electronic and thermal conductivities as well as the impermeability to gases. So the material that we wanted to get is actually to become more lightweight, thermal and more conductive. So the application that we can see here is actually for supercapacitor, conductive wires, flame retardant, coating, and as well as premium gloves. However, there's a few drawbacks here because we still suffer a major drawbacks in terms of stability and in case we use solvent as well. So so the challenges we face here is actually we want to get it more low cost and environmental friendly technique, and as well as the transformation of the current traditional manufacturing is quite difficult for us to penetrate the current industry. So this is the forcing industry that we can explore, especially on the transportation, for petrochemical, construction, communication, and electronics, health, especially in for premium gloves or high value added gloves, big products such as catheters and also condoms, and as well as engineering components and defense. So this is the experimental method I will discuss with you briefly. So the nanotubes is a nanotubes dispersion prepared with the surfactant we selected. So we stir it overnight. Then we compounded the latex and left it overnight for drying in the ambient temperature. Then we cure the film and we characterize the film for the mechanical, electrical, and other other tests. So here, since I will going to discuss with you on the surface analysis, so let me bring you to the film formation process. So here we actually, I already draw out for you how is the film formation process and why do we get one part isolative and the other part conductive or semiconductive. Okay, so this is you can see there the carbon nanotube dispersion. Then during the film formation process, the water will evaporate and then the particle will get in close contact and start to arrange themselves. So after that, the carbon nanotube and the latex particle must coalesce in order to overcome the heteroeffective repulsion interparticle stabilization forces. Okay, because you have to understand here, because the carbon-carbon material and as well as the polyisoprene and together with the surfactant. So that is the effective repulsion that is actually occurring during the drying time or the film formation process. So for a long time, we actually allow the incorporated carbon nanotubes to arrange themselves within the latex matrix to form the connecting network. So this is important to get the conductive uh, properties from this side because of the connecting network is crucial. So the successful film formation will actually obtain by the diffusion of the latex and the carbon nanotubes across the particle interface. So this is actually due to the hydrophobicity of the carbon nanotubes or the van der Waals forces. That actually makes the film conductive. Okay, so this is the illustration of the TEM image here that I'm sharing with you. So this is during the film formation process. So the latex are actually destabilized and coagulate into a continuous network structure by the physical entanglement of the nanotube between the polymer and the encapsulated protecting layer, as in this case, which is the natural rubber latex or the polyisoprene. Okay, so I'm sharing with you the 2D surface morphology of the film. So on the left, you can see the white patches there. So that is the non-conductive, and whereas, the white patches, whereas on the right is the conductive. Okay, so you can see the on the right, which is the dark image representing the non-conductive, whereas the white patches is actually illustrating the conductive shades. or the conductive properties. Okay, so whereas on the figure 2, the 3D images, the left you can see which is the spherical structure of the latex, and whereas on the right you can see the bumps there, the white patches there is representing the conductive images. So you can see the scan area. So the height is about 1 micrometer. So it's believed to be the size of the round particle there. So it's believed to be the individual latex particle. Okay, so this is the conductive AFM. This is by using a non-contact mode. So you can see the non-conductive and also the conductive, which is on the left, and whereas on the conductive is on the right of the cast natural rubber film. So I know it's not actually dispersed well, so because probably it's coated by the thicker particles of the natural rubber latex embedded on the film. Okay, so this is the conductive. This is by using the contact mode. So you can see it's not it's quite clear which is for the on the left, but on the right for the conductive one is not that clear. Okay, so you can see the difference between these two structures, whereas the white patches there is actually illustrating the conductive side of the film. Okay, as for the conclusion, what I can say here, AFM analysis of the nanocomposite can be a good alternative to electron microscopy without some limitation regarding about the contrast and also the resolution. So AFM does not require a conductive coating at most of the time staining. So AFM also can also measure the fundamental properties of the sample surface like local adhesive and or also elastic properties, especially for the polymeric study in nanometer scale. Okay, with that, I thank you.